Hi, we are Sania González Telles and Maria Jose Chaboya Zamora, and we are going to present diffraction grating. This is the outline of our presentation. The objective is to study Fraunhofer diffraction through multiple slits, and the specific goals are to obtain the experimental values for the wavelength of the radiation and the distance between its apertures using the diffraction condition, and also to compare the results obtained.
Now, diffraction is the spreading of waves around an obstacle due to interference, and diffraction grating is considered when we have four or more apertures. And according to the Huygens principle that states that every point on a wavefront may be considered as a source of secondary waves, we are going to derive the following. But first, as we can see in the first image, we have a grating that has a zero order mode, where the integer order of diffraction m is set to 0, in which the rays of light behave as according to the laws of refraction or refraction. And in the figure, we can see an ideal diffraction grating setup that is made of a set of slits, and each slit is with a spacing d. And that spacing must be wider than the wavelength that we are going to use, therefore, so it can cause diffraction. Now we're going to assume that a plane wave of monochromatic light of wavelength lambda at the normal incidence on a grating, each slit of the grating acts as a quasi-point wave source from each light, also meaning that each light propagates in all directions, as we can see in the diagram. And after the light, the incident wave interacts with the grating, the resulted refracted light from the grating is composed by the sum of interfering waves components emanating from each slit in the grating. So at any point in the observation point, the path length from each slit of of the grating to the point varies because we have different path differences. So the phase emanating from each of the slits at the point also varies. And as a result, the sum of the diffracted waves at the given point creates constructive and destructive interference. And as we can see in the second diagram, we can see better explained the path difference that is emanating from each of the grades of the diffraction grating.
Now, when the difference between the light from the slits to the observation point is equal to an odd integer multiple of half of the wavelength used, we are going to obtain that the waves are out of phase and therefore they will cancel each other to create the minimums of intensity. While in the other hand, when the path difference is a multiple of the wavelength lambda, the waves are going to be in phase and then we will find the maximums of intensity that will occur at different diffraction angles, theta m, where m is the order of the maximum. Now, the diffraction condition for a plane light wave that is normally incident on the grating is given by equation 1, while if the plane wave has an arbitrary angle to the grating equations becomes equation 2, and we will find the maximums of of intensity when the angle theta of the different maximums is given by equation 3.
Now for the materials used in the experiment, we used a red diode laser, the rail, diffraction slits, millimetric paper, and measuring tape. As we can see in the image, which is the experimental setup that we used, which was the Pasco high precision diffraction slits. And as we can see, the experiment consists of placing multiple slits in front of monochromatic light source at the end of the optic tract, and far away from the slits, the observation screen is placed so we can analyze far field diffraction. When the beams of the light passes through the slits, it is diffracted towards the screen, and there it is possible to observe the diffraction pattern, which is presented in the figure below. For the first activity, which is where we obtain the wavelength, the diffraction condition relates to the position of maximums of their order, where y is the distance from the central maximum to the maximums of order n. So as we can see in the first table, we have the values of the distances y and the order m. Then we were able to obtain the sine of theta by dividing y over d, and then we multiplied this by the slit separations D, as we can see in the second table. And then we obtain the uncertainties related to this table in the equation below. And with the data obtained in the second column of the previous table, we plotted it as a function of the orders m, as we can see here. Therefore, we were able to obtain, we did a linear adjustment where we were able to obtain the wavelength using the slope. And the wavelength obtained of lambda was 653 plus minus 5 nanometers, and we compared it to the manufacturer's manual of 650, and we obtained an error percentage of 4.46%.
Now, to obtain the separation between slits, we once more use the values of the distances from the central maximum to the maximums of order m as presented in the first table, but we also use the quantity in the third column given by y divided by the distance from the slits to the observation screen. And the error associated to this column was given by this equation 7. And now to obtain the separation between slits, we have to rearrange the diffraction condition as we can see in equation 8. Then using equation 8, we can plot the maximums of, the order of the different maximums as a function of the third column of the last table, y divided by d. And we could also use a linear approximation where the slope of this linear approximation will be the separation between slits between the wavelength lambda. Here in this figure we can see the values plotted and the linear adjustment. We obtain a slope of 189 with an error of 2. And then using the slope, we obtain the value of the separation between slits that was 0.123 plus minus 0.001 millimeters. We obtain the error associated with this equation. And we compare this value with the real one that was 0.125 millimeters, and we obtain an error of 1.6%. Now the observation. We observed for activity 1, we observed that the data obtained was not really dispersed and had a strong correlation. This allowed us to obtain an acceptable result, which was really similar to the one given by the manual. And we also can take into account that the wavelength of a red laser can be between 630 nanometers and 670 nanometers. So we conclude that our result is within the ranges. And for activity 2, we once more obtained that the data had a strong correlation. This gave us a reliable experimental result. And we believe that we can improve our result by taking into account maximums of higher.
And for the conclusions, for the first part of the report, we studied diffraction grating with multiple slits, and we successfully proved the diffraction condition and obtained an experimental value of the wavelength of lambda of 653 plus minus 5 nanometers with an error percentage of 0.46% compared to the manufacturer's manual. Later, for activity 2, we analyzed the data to obtain the experimental value of the separation D by using the diffraction condition, and we obtained a value of 0.123 plus minus 0.001 centimeters, and with an error percentage of 1.6% compared to the manufacturer's manual. And these are the references we use. Thank you.